Cool, let's get started. So hi everyone, welcome to the Control Meets Learning seminar. Today we are honored to have Professor Necmiye Ozay from University of Michigan. Professor Ozay received her bachelor degree from Boğaziçi University, Istanbul in 2004, her master degree from the Penn State University, University Park in 2006, and her PhD degree from the Northeastern University, Boston in 2010, all in electrical engineering. She was a postdoc scholar at Caltech between 2010 and 2013. Then she joined University of Michigan in 2013, where she is currently an associate professor of electrical engineering and computer science. She is also a member of the Michigan Robotics Institute. Professor Ozay's research interests include hybrid dynamical systems, control, optimization, and formal methods, with applications in cyber-physical systems, system identification, verification, validation, autonomy, and dynamic data analysis. Her paper has received several awards, including the Nonlinear Analysis, Hybrid Systems Prize Paper Awards for the year 2014 to 16. She has also received 5 Young Investigator Awards, including the NSF Career Award and several other awards from the University of Michigan for her contribution to teaching and research. So today, Professor Ozay will talk about learning models and constraints with limited data. Without further ado, Necmiye, the floor is yours.
Thank you so much, Yuan, both for the nice introduction and for inviting me to speak. Today I will talk about learning models and constraints with limited data. Maybe this is going against the big data buzz out there, but I will try to introduce some control problems where we might not have too much data and we should be able to do something with limited amounts of data. So a quick outline of the talk. I will give an overview of some problems at the intersection of learning and control where this limited amount of data is what is relevant and what you should work with. Then in the first part of the talk, I will present some results on sample complexity analysis of linear system identification. And I will present an analysis of the Ho-Kalman algorithm. And in the second part, I will show something more practical and I will discuss some learning from demonstration type problems in the context of robotics, where we are trying to bring some control concepts and we are trying to do something like inverse optimal control, again, pioneered by Kalman. This is kind of control 101. So typically in all control problems, we have some model of the plant that we want to control and we have some task specification. Through the years, the control community developed lots of methods for designing controllers, given the models and task specifications, so that when we close the loop with this controller, our closed loop satisfies this task specification or the requirement. And now what we are trying to do these days is to bring in data to this picture. So you can bring data to this picture in 2 different ways. You can still be model-based. You can take your data and go to a model as an intermediary. And you can design a controller from using your traditional tools. And I will be more on that camp because I think we have very powerful tools in control and we should sort of leverage those tools as much as we can. Or you can be on the model-free camp and you can go from data to directly control. So as I said, I will talk mostly about this pipeline where you go from data to models, then to control. And in the first part, I will assume task is given or task might be changing. And I will go from data to models. I will be in a setting where data is limited in the sense that, for example, you are exploring an unknown environment like Mars. You cannot collect experimental data a priori. You want to send your helicopter there, maybe fly it a little bit, and during that process, you should identify your dynamics. And based on your dynamics, you can decide on what the capabilities of the system is, and you can proceed. Or there could be more extreme cases where there's an unexpected failure, as in this blown up engine on the right, where you need to identify this new dynamics fast enough, and maybe you need to figure out what the next task you can achieve, given that you have a single engine. So this would be one of the settings where I want to online collect data and learn the model at runtime as fast as possible. Then based on that model, someone gives me a task and I will decide whether that task is achievable or not. So the other setting is going from data to a task, assuming we have a model, and learning the task from data. And this is relevant in teaching a robot to do something new. And especially if you think about an inexperienced user, an end user trying to teach new tasks to robots, you don't necessarily have too much data, and you don't want your user to spend too much time trying to teach the robot something. So you want to kind of be sample efficient and learn from small number of demonstrations. What is the task? What are the constraints? And possibly with this task or constraint description you have, you want to generalize and perform the same task in new environments. Again, this is a setting where you might not have too much data, and the user might not have, it's not efficient to collect too much data. And I will try to present two different methods for the first setting and the second setting. And I will start with this sample complexity of linear system identification. So linear system identification, it has a long history. So we are given some input-output data, and we are trying to learn a model of this form where I have my A, B, C, D matrices, maybe corrupted by process and measurement noise. And this A, B, C, D are unknown. Those are the things that I am trying to learn. And these noise values are also unknown, and they are not measurable at runtime. And I am measuring my inputs and outputs. And in the literature, there's quite a bit of analysis in the asymptotic regime. So system identification community studied this problem and analyzed as the data size n goes to infinity or these noise levels go to 0, can we learn the system model? Or what are the things we can learn about the system in the asymptotic regime? So what I will be interested in this finite data regime is the non-asymptotic analysis. So given that we have to work with finite amount of noisy data, how does this identification accuracy depend on the data size and noise level? So that's the type of question that I want to answer. And what can the best identification algorithm achieve in this case? So kind of lower bound type ideas are the things that I am interested in. And I want to understand what makes a system easy to learn or what makes a system harder to learn. So there are quite a bit of existing results, both for asymptotic analysis and some old and new results for the non-asymptotic case. And you can get textbooks for asymptotic analysis on system identification. And on the non-asymptotic side, there are control theoretic methods based on sampling type ideas that try to get numerical numbers on how much data you would need to learn your model. There's also this new interest in the problem from statistical machine learning community that are bringing in some new tools and trying to understand the sample complexity and the dependencies of learning rates to system parameters. And most of the results in the control theoretic methods, they tend to have different assumptions. One of those assumptions, for example, there's this very nice recent review paper by Carré et al. One of the assumptions they have is noise invertibility. So it essentially requires, given the noise term, given your system model, whether you can find the noise if you knew the system model. And under that assumption, there is quite a bit of literature on giving you this sample complexity. That assumption doesn't hold in our setting, so those results are not directly applicable. On the statistical machine learning side, the focus was on the case where, at least initially, the focus was on the case where you observe your state instead of your output. And if you observe your state from a system identification perspective, things are a little easier, although the analysis itself is still challenging. But it's clear what you are learning. You have a simple least squares problem, simple to write at least, but it's still a challenging problem to analyze due to dynamics and dependency. And we want to move from that state measured case to a case where we have input-output measurements, and we want to use or analyze existing system identification algorithms. Rather than coming up with a new algorithm, there are algorithms used out there. Can we bring in these tools to use for traditional system identification algorithms? So that was our original motivation. And the plan for the first part of the talk, we will focus on a well-known system identification algorithm due to Ho and Kalman. I will introduce this algorithm. I will show you some sample complexity analysis of this algorithm, where we will give provable guarantees on the accuracy of the model as a function of both some parameters of the model itself and some number of samples. And I will also discuss this noise sensitivity of or robustness of Ho-Kalman algorithm, because that was something needed for our analysis, and we were surprised to see that that doesn't exist. Okay, so let's look at the Ho-Kalman algorithm again. Remember, our goal was to learn this ABCD in the noisy setting. However, the original Ho-Kalman algorithm was developed in a very algebraic way in the noise-free setting. Then there were extensions called ERE, I forgot the acronym. So that there were extensions that extended this algebraic analysis using SVD to work with noisy data. But there are a few challenges if you start looking at this input-output model. The first problem is that identification problem is ill-posed. So we can only learn things up to a similarity transformation. And if you have a control background, this should be clear, because if I have some A, B, C, D, and if I define a similarity transformation and change my state, since I don't know my state, I can just write down the dynamics for X tilde, I will get a new A, B, C, D. And there is no way for me to differentiate this original A and this other A that's just an equivalence transformation applied to my original A. So there's this ill-posedness thing, and we should really pick a representation. So if you observe the state, the representation is clear, but if you are doing input-output system identification, you need to pick a representation. Then depending on your representation, you need to pick an algorithm to learn that type of representation. And you can analyze that algorithm that learns that specific representation. So the other thing that we know from classical control is that we can only learn the controllable and observable part of a system. So if there are uncontrollable and observable things, we cannot learn them. So for simplicity or almost without loss of generality, we will assume the system is controllable and observable. If not, we are just learning controllable, observable part anyways. So to apply Ho-Kalman, we will follow a two-step procedure. And the representation that we pick is none of the canonical forms. So there are canonical forms for ABCD, which are like controllable canonical form, observable canonical form, and so on. Instead, our representation would be the impulse response of the system, which is the Markov parameters of the system. And these Markov parameters, if you think about the similarity transformation that I just showed, these Markov parameters is invariant to the choice of that similarity transformation. So no matter what underlying system is, these Markov parameters, D, CB, CAB, CA to the K, B, those would be uniquely determined independent of the internal representation. So this is going to be the representation we will try to learn. And given this representation, from this representation, we can construct an ABCD. And the ABCD that we will try to construct from that representation would be the so-called balanced realization for the system. So Ho-Kalman really focuses on the second part in the original paper. So I will first introduce that process. Then I will go back and tell you how we can learn this Markov parameters or impulse response from data with sample complexity guarantees. Okay, so here is how Ho-Kalman algorithm works. Assume you are given these Markov parameters, you know the impulse response of your system. You form a Hankel matrix of these Markov parameters. This is this matrix with log anti-diagonals that are constant. So these anti-diagonals are constant. I don't know if you see my cursor. So you form this matrix. This is called the Hankel matrix of the system. And one nice thing about this matrix is if you look at it carefully, this matrix, you can factorize it into an extended observability matrix and an extended controllability matrix of your system. And from this factorization, you can see that the rank of this matrix for a controllable observable system, it's always n. And this n is your state space dimension. So what Ho-Kalman did is they picked this submatrix, excluding the last column of your Hankel matrix. This is another Hankel matrix. And again, since this is a similar Hankel matrix, this has a factorization in terms of extended controllability and observability matrices. And they also consider this other matrix. This is also a Hankel matrix, but it's slightly different. It's your observability matrix times A times some extended controllability matrix. And if H plus is defined this way and H minus is given this way, then you can do a singular value decomposition to construct an ABCD. So what you do an SVD to H plus. So this is rank n. So this is an exact SVD if your data is clean. And then you pick your observability matrix. So this L is the, essentially in this case, it's equal to H plus, but in the noisy case, this is gonna be the SVD truncated version of H hat plus. Then you set your observability matrix to be U times your singular values to the 1/2, and you set Q to be, again, your singular value matrix, diagonal matrix to 1/2 times V transpose. Then you set your C bar to be the first M rows of O. If you remember your observability matrix, first M rows is your C. You set your B bar to be first P columns of Q, and using this relation down here, given H minus O and Q, you can solve for A bar as well. And if you note here, the singular values of this Hankel matrix are called Hankel singular values, and they are very important in realization theory. They roughly tell you how controllable and observable different parts of your system is. And since controllability and observability is required for identifiability, they also tell you how identifiable your system is. And the CBA bars are called a balanced realization, where essentially you are finding a similarity transformation in a way that each state is equally observable and equally controllable, so that you can use this for model reduction, or you can use this for figuring out the order of the system if you didn't know the order of the system. Or order of the controllable observable. So what we will do, as I said, we don't have the Markov parameters, but we will estimate them. So instead of this actual H, I will have some H hat. But I will do the exact same process. Instead of an exact SVD, L hat would be just this SVD truncated at N. And I will form my O hat, Q hat using this truncated SVD by setting the singular values after the nth one to 0. And I will compute my B hat, C hat, A hat accordingly. Now, the first question that we asked is, so this is a process that's used a lot in practice. It's used especially in structures and civil engineering, where you have this like very high dimensional systems that you are trying to identify. And we wanted to understand, okay, this process works in the limit, or if you have your Markov parameters, but if I am making errors in my Markov parameters, how much of an error I am making in my system metrics estimate? So this is the question that we want to answer. If I knew how much my estimated Markov parameters deviated from the true Markov parameters, can I say anything about how much this ABCD estimate that I obtained from this algorithm will deviate from the true ABCD? And one thing we can show, since this H and L are constructed using G, the error in H, measured in spectral norm, is just some factor times G minus G hat. And this factor is how I am picking the number of rows and columns of my H. And I should make sure these are at least N, so that I capture all the modes of my system. And given this, we can also construct error values for our estimates A, B, and C, assuming the error that we are making in L is less than the minimum singular value of true L, which is essentially telling you whether my system is how identifiable my system is. Then we can ensure that the ABCD that we construct is similar to the true balanced realization. And this is how much error you are making. And essentially, this makes lots of sense in the sense that if the smallest non-zero singular value of L is large, then it means my system is more controllable and observable, and I will be more easily learn my ABCD. And if this gets smaller, then the system is harder to identify, and I will make more error there. So there are, I think, some questions in the chat. I can, if
yes. Konstantinos asked about how large should T1 and T2 be?
So they should at least be n, but then you have flexibility in picking those as long as they are larger than n. And their sum is the number of data points that I will be using in my algorithm. And I will come back to that. To the bound on G minus G hat will depend on the sum of T1 and T2.
Yes, and we have two more questions. Ram is asking, is there a particular procedure to estimate the Markov parameters since they're being used to estimate H and L?
So that's going to be the next thing that I am going to discuss.
Great. And Isong is asking, the assumption of observable and controllable means the relevant control problem depends only on Y and not the rest of the X, right?
At this point, there's not really a control problem. But it's just saying these are the things that I can really manipulate in the system, given that my output is what I am observing. So if I have the chance to add more sensors and stuff, I can maybe solve other problems. But it's true in the sense that with this system, this is the part that I can manipulate. So I can only solve control problems relevant to this part. If I have other control problems where I have uncontrollable, unobservable pieces, and my control objective requires me to manipulate that, it's going to be much harder. But at this point, we don't have a control problem. I am just interested in learning the dynamics. So stability of A will come into play in learning the Markov parameters. I will answer that in a bit. Okay. Now we have some bounds on stability of this Ho-Kalman. So if I could estimate my Markov parameters good enough, I know I can estimate my ABCD. So the question is, how do I estimate the Markov parameters, as someone in the chat, I think Ram asked in the chat. Okay, so two things now. We have noisy data and we need to estimate these Markov parameters. And we will assume the following. We will assume our initial condition is 0. So this is easy to relax. Although we don't observe this process and measurement noise, we will assume they are Gaussian and we know their variance. And we will also assume we are deriving our system with a Gaussian input with some known variance. So actually Markov parameters are essentially equal to expected values of these type of cross terms. So if I have yt ut minus k, this is going to give me my kth. If I can compute the expected value of yt ut minus k and scale it with my input bound, this will give me my Markov parameter. But the problem is that I don't have a good way to estimate this expected value. I cannot do simple sample mean type tricks because if I want to do sample mean, I need independent variables. And since I have a single trajectory, everything is dependent. So I don't really have many terms to estimate this thing. So we cannot use the sample means to estimate expectations directly. So what we will do is we will try to recast this as a least squares problem by looking a bit carefully into our system variables. So my y of t at a given time is a function of my x0 and my inputs from u0 to ut. Similarly, you can write your y of t plus 1 as a function of x1 and your inputs from 1 to ut plus 1. And you can do this all the way through yn bar, where n bar is the number of data points that I have. So given this sequence from 0 to n bar, I can divide it into subsequences of length t plus 1. And I can write how the subsequences, how the y of these subsequences are as a function of x0, or the first x at the beginning of the sequence, and the inputs down there. So this is, again, simple solutions of linear systems. If you have taken any linear system theory course, you will see how this works out, or you can write it down recursively. But we can essentially write y of t as c e a to the t times this x at the beginning of the sequence, plus some u-dependent terms, and some terms that depends on my process noise all through the sequence, and my final measurement noise. So I can write my y in terms of this unknown x, unknown w's, unknown z, and known u. And I can just collect things together. This is going to be yt is equal to some g matrix, which you should recall from the previous slide. This is essentially a matrix of my Markov parameters. Some f matrix. This f matrix is essentially related to your observability matrix, containing the CA to the K type terms, this Z, and this E, which we put as the effect of this initial condition of the sequence. And this effect of the initial condition, to make sure it remains bounded, we will require A to be stable, because if A is unstable, then this effect will blow up and I won't be really able to see the Y clearly from what I know in the system. Now, what I will do is I will just write down a least square problem. I will assume everything here is noise. Then I end up with yt is equal to gu plus noise. So I can write down my least squares problem, and my g estimate would be the minimizer of this least squares problem. So find x, which x is this set of Markov parameters that minimizes this. So the question is, how good is this estimate? So that's the question that we want to answer as a function of this n bar and other system parameters. So if we look a bit closely to this thing, I can write this least squares problem in matrix form, just concatenate all n observations, where this y is from initial y to final y, where I have this u, w, which are Hankel type matrices, and I can write my y in this form. And I can also, in closed form, solve for this least squares problem, because this w, z, e terms are not there. I just need to do a pseudo inverse to u to get my g hat. So y times u pseudo inverse will give me g hat. But if here I plug in the true y, this g hat, I can express it in terms of the true g and the other terms that appear in my equation. Then the error would be just induced by this term. And if I understand what this term, how this term evolves as a function of samples, then I understand how my error evolves as a function of samples. And we will try to bound these different terms. And to bound this first couple of terms, this one, the green ones, you can use some concentration inequalities based on circulant matrices. Since these involve Hankel matrices, you can always embed a Hankel matrix into a larger circulant matrix and use concentration inequalities there. And there's some martingale argument to bound this term with high probability. So we can bound all of these terms with high probability. And overall, if you combine everything, what we can say is that with very high probability, that tends to 1 exponentially as n hat goes to, that tends to 1 exponentially in n hat. This g minus g hat will have this much error. So it's useful to look into different terms here. So essentially we have 3 different effective noises, and this is your signal to noise ratio. So if I have larger inputs, my error will be smaller compared to the noise. Then there's some effect of process noise here. So it's just the variance of this or standard deviation of this process noise. The effect of, measurement noise, Z. The effect of process noise is multiplied by F. And if you remember F, it's your observability metric. So you can think about this as your observability gradient. So this is essentially how much this W affects your output. And there's this square root of N0 over N term, which means your accuracy as a function of number of samples is order n to the power -1/2. So you can combine these different things. Then for given delta and epsilon, you can find an n bar such that if you have data of length n bar with high probability 1 minus delta, with probability 1 minus delta, you can estimate your system matrices up to an accuracy epsilon. And similarly, given some n bar, you can find a bound epsilon on the accuracy of the system matrices with probability 1 minus delta. So combining these results, you can go both ways. And there are several extensions. You can estimate H infinity norms, H infinity norm error in the models that you are estimating. You can estimate system order, etc. So let's look at some numerical examples. So we know Ho-Kalman works, but it was interesting to see how the analysis comes into play. And there's a slightly different analysis my collaborator Samet did in a slightly different context to handle this dependence that makes your analysis hard. What he did is, okay, let's wait a little bit. Instead of taking all of these samples, let's wait a little bit in between where we are taking samples, and let's assume those are almost independent. And you can do very similar analysis, come up with very similar sample complexity results. But in practice, if you increase that separation, your error will increase. On the other hand, we are using all the data. So we are being both practically we are using the data better, and we have similar tight statistical bounds. So there are more recent results. So this is still an active research area. This is an incomplete list. As I said, we have this stability assumption. I think if you have single trajectory and process noise, there's no way around that stability assumption. But if you assume you have multiple trajectories, then there are methods that work with unstable systems as well. Essentially, if you have multiple trajectories and at each time you can put your system initial condition to 0, you can still learn the system. The rates are more or less similar. And the other thing is number of samples needed for these rates to work. In our work, T is the number of Markov parameters that we are estimating. So, and P is the number of outputs. So our results work as long as you have P times T samples. And this is essentially to make sure your least squares problem is not underdetermined. So there is an interesting result where instead of least squares, if you start doing regularization with nuclear norm, instead of your dependence to Markov parameters, you can have dependence to system order, which is much better. But for that, at this point, at least you need multiple inputs. And there's another result that works with stable systems, also unstable systems that uses multiple trajectories and still uses this Markov matrix estimation. And there's this other result which uses the property that your Markov parameters are almost sparse, because larger Markov parameters for a stable system is almost 0. Then essentially it's enough to look at logarithmically many Markov parameters and assume the rest are 0. And you can get similar rates, maybe a little low. Okay, now I will switch to the second part. This is going to be a shorter part in the last 10 minutes, but if there are any questions, I can take maybe a quick question, or we can wait until the end. Okay, I will continue with the second part then. So as I said, there's this other setting where we might have not enough data because we don't want to demonstrate thousands of times for a robot to do something. I would rather go and do it myself if every time I need to show the robot to do things thousands of times. So this is, so what we want to do is we want to learn constraints from demonstrations, and the standard inverse optimal control setting is you want to learn a cost function from demonstrations. So here instead I want to learn constraints. And why constraints? Because I feel constraints are more modular and explainable. I forgot who said this, but an HRI person said this. Humans don't think in terms of objective functions. So they usually think about, oh, what are the constraints? And if we have constraints, we can again use them for control design and give some system level guarantees. And one challenge here is that, as I said, you might not have too many examples, and all the examples you have are positive examples in terms of constraints. So you cannot like break stuff and say, oh, this is a demonstration that violated my constraint. So those are the two challenges. Again, there's quite a bit of work, especially in learning cost functions. So inverse optimal control is followed up with this inverse reinforcement learning in more stochastic settings. There is work doing constraint learning, and we will also try to extend it to multi-stage tasks using temporal logic type formulas. So let's look at our problem setting. So we assume we have a demonstrator that solves some optimal control problem. And there are things in this problem that we know, and there are things we don't know when we are observing trajectories. So these are two demonstrations. In the simplest case, a 2D system. And there is this red constraint that we are not aware of. So the cost function, we don't know. We just have a parametric form. There is maybe some task-dependent constraints that we know. In this example, maybe we know initial and final points. So that's something we know. Maybe there are some shared known constraints. These could be my dynamics. I assume I know my dynamic model, and if I am solving this optimal control problem, dynamics will be in the picture. And for example, dynamics and input bounds as well could be that shared constraint. And there's this unknown constraint, this unsafe set that I don't know. And I am observing these demonstrations, and I want to figure out what this set is. And we assume there's a parameterization of this unknown safe set. So these trajectories are in some safe sets. S, where this obstacle in this case is the unsafe set, which is the complement of our safe set. This A is unknown safe set, and there's some parameters, and I want to learn the parameters. So our problem is, given n locally optimal demonstrations, we want to find these unknown parameters that make each demonstration locally optimal. And given those, we want to be able to plan some guaranteed safe trajectories in the environment, given different tasks maybe. We want to figure out what parts of the state space is guaranteed safe and what part of the state space is guaranteed unsafe. And the tool that we will use is, since these are optimal demonstrations, locally optimal demonstrations, they should satisfy Crash-Tucker conditions. So this is the demonstrator problem, and we know the solutions to the demonstrator's problem should satisfy Crash-Tucker conditions. To write them in terms of Crash-Tucker conditions, I will take the set description of the problem and I will put it into a functional description form. So there are some unknown constraints parameterized by theta. There are some known constraints, inequality constraints and equality constraints. And equality constraints are usually my dynamics in this case. And I can write down my Crash-Tucker conditions. Given this demonstration, I can just plug these in. So there's primal feasibility. Lagrange multipliers are things that I don't know. And this theta and gamma are the things that I don't know. And it turns out that if I write down these Crash-Tucker conditions for each of my demonstrations, and if I can find a consistent gamma and theta, then that would give me a set of consistent constraints. Of course, this says these constraints are consistent. They are not guaranteed safe or unsafe at this point. If I want to ensure guaranteed safety or guaranteed unsafety, I need to make sure these constraints are feasible for all. So essentially, I need to understand the feasible set of this problem and project onto gamma theta domain to find the guaranteed safe regions in my problem. And we also have some geometric analysis of what is learnable. So this is a very ill-posed problem. Although optimality of the demonstrations gives you quite a bit of information, the things that you can learn is still limited. And how well it works in practice essentially depends on whether your constraint parameterization is close to the real thing as well. And how do we solve this problem is another question. So this is essentially a mixed integer linear program for some cost and constraint parameterization. So if you have your constraints are unions of boxes or unions of zonotopes, we can recast this as a mixed integer linear program. So we have applied this in a few different contexts. So I have some robotic manipulation examples here. So you have some glasses and you are carrying a heavy object. Maybe you don't want to go over the glasses with the heavy object. And you can learn these type of elliptic obstacles. Here is a bartender type task where in a VR environment, we gave some demonstrations to our robot. Here, we only have 5 demonstrations, and there's this pose constraint since we are serving something to a person. Maybe I am serving something in a cup. I don't want to flip it too much. So we are learning these pose constraints, and we are also learning the locations of things, how close we can get to the human, and with the learned constraints we can plan. We have some examples where, again, here I have my demonstrations, 5, 6 demonstrations, and I have a high dimensional quadrotor, again, some pose constraints and workspace constraints, and we can do planning with these type of things. So this seemed to work quite well. Then we were interested in seeing whether we can extend this to multi-stage tasks. Instead of go from one point to the other, can we do something like, oh, fill in the glass, grasp the glass, deliver to person. So you really have this high-level discrete planned part of things as well. KKT is more low-level. It looks at local optimality on the continuous part. But here there is some discrete decision-making going on as well. And again, the problem is we have only a small number of positive demonstrations. So the question is, can we learn this multi-stage constraint tasks? And using that learned representation, can we complete similar tasks in new environments? So it turns out that we can do one other trick in addition to KKT. But here we need global optimality of the demonstrations. If I know my demonstrations are globally optimal, then if I just look at the constraints that I know, if I generate any trajectory that has lower cost, that trajectory is violating something. And that gives us a very cheap way of generating negative examples. We don't need people to make errors as long as they are optimal. They are essentially telling us what is infeasible, and we can generate these unsafe trajectories. And for the multi-stage task, we encode it using a parameterized version of linear temporal logic. If you don't know what it is, don't worry about it too much. But there's a grammar of this thing that's represented with a syntax tree where you can encode your high-level plan. And there is a parametric part where you can encode the geometry of the objects that you are interacting with. And here are some examples. For example, the green one that fills the glass, picks the glass, and delivers it, satisfies the formula. There is a simple path, the red path, that goes directly to the person. But if I know the green is globally optimal, I can say this red one violates the constraints because it has lower cost and the person didn't demonstrate that. And again, this grammar and geometry part, they don't mess up with our mixed integer linear programming framework, and we can write everything down as a mixed integer linear program. So here's an example. We had a VR environment where we are showing a demonstration where we want to grab the soup. There should be a Campbell soup somewhere. So we are grabbing the soup, placing it into a small box, then delivering it to the blue region. And the robot doesn't know what this task is. It's just observing what is going on. Then we want to take the Cheez-It and we want to deliver it to the green region. Again, the robot doesn't know what the task is. It's just observing what things we are interacting with. And while doing this, we want the end effector to be upright so that we are not spilling anything. So in this VR environment, we show the robot this demonstration. Then we set up a similar environment in real life. The objects in the environment are the same, but the places of the objects are different. Since we are learning the task, if the environment changes, my task doesn't change. And we can, for some reason, video is not playing. I don't know if you can see the robot. Okay, it shows up there. Okay, let me try to play this again. Okay, now it's coming. It's a bit slow. It's gonna pick up the Campbell soup, put it into the small box, and deliver it to the blue pad, I think. then it will take the Cheez-It and put it in the larger box. Okay, this is the end of this part of the talk. I can take questions here, and while the video is playing, then I can quickly summarize some of the things that we did and some of the open problems that we are playing with.
I have a question. Do you see a way to relax the global optimality assumption? Because to me, seems like the reason we can learn this constraint is each demonstration is around the boundary of the constraints. So what if we are a little more like conservative? We are kind of not locally optimal.
So that's a very good question. There are two ways of doing it. One is a practical way. The other one is a more theoretical way. You can essentially, practically what we do is we relax this conditions of being equal to 0 in our KKT conditions, and we just put some select variables here. And we say minimize those select variables and make these things as 0 as possible. And that works in practice, but then it's not like what is guaranteed is a little bit of a question at this point. So from a practical standpoint, since we are collecting these demonstrations in VR, they are not really locally optimal. They are deviating a little bit. And just relaxing this equality constraints a little bit works in practice. So there is a way to encode if you know you are epsilon suboptimal, you can encode it in KKT directly, that epsilon suboptimality. But the problem is that we don't have a mixed integer convex way of, like, you get non-convex problems in that case. And we couldn't figure out yet a way to get around that non-convexity with a relaxation or anything.
Okay. Yeah, I also have a related question since you mentioned about like learnable parameters. I mean, like if in the demonstration like a constraint is never bounding, like does like that parameter is not learnable, right? But how can we detect that since we only see this trajectories, so we don't know like which constraint like are binding where we have seen, yeah.
So the thing that will happen is that one thing you can easily detect is if I ignore my unknown constraints and assuming I know the cost function, and we assume the cost functions in these cases are simple. It's just shortest path or shortest time. And all the task relevant things are captured in the constraints. So if I solve the known part of the problem and if I get the same solution as the demonstration, then I know that that demonstration is not activating any of my constraints. But the parameterization of the constraint is important. So there's one other thing you can do. For example, if your constraint parameterization is under-parameterized, say you have 10 boxes in your 10 obstacles, and you said, oh, I will just try to explain everything with a single box, then this KKT problem becomes infeasible. So there's that, if this KKT problem ends up being infeasible, you know your parameterization is insufficient. If KKT problem is feasible, then you don't really know if your parameterization is sufficient. You just know there are some environments where these demonstrations are optimal. So we have some analysis of learnability. So if you don't, for example, if you don't assume anything about these constraints, you can only learn extreme points of obstacles in the workspace, or you can learn skeletons. But if you make more assumptions on what these constraints look like, if you say, oh, workspace obstacles are convex, or it doesn't really need to be in the workspace. So it could be some other space, but you need to know that mapping to that other space, and you say, okay, in this other space, which could be a nonlinear mapping, my constraints are just unions of boxes. You can, or unions of zonotopes. You can get around with that. But there's again a representation problem here. If your representation is bad, then you cannot really do much.
Thanks. And there is a question in the chat box by Sango, ask for the system ID part. Is there any lower bound result for sigma mean L? Like, yeah, and is it independent of the size of the Hankel matrix?
So for the clean data, sigma min L, it's independent of the size of the Hankel matrix, and it's kind of related to your controllability and observability gradients. So it's related to the minimum singular values of your controllability and observability gradients. So that's a well understood quantity in the noiseless case. Okay, maybe I can finish with a quick advertisement. So if you're interested in these topics, we are putting together a special issue in this Journal of Mathematics of Control Signals and Systems on topics related to control and system identification and data, together with Alessandro Ciso, myself, Mario Schneier, and René Vidal. So the submission deadlines are in August, September. I think it goes from August to November. So if people are working in this area, I encourage you to consider submitting something to the special issue.
Okay, cool. Thanks so much, Professor Ozay, for this awesome talk. So if anyone have any questions, feel free to ask now, or otherwise we all like end the talk. Okay, cool. So for next week, we're going to have Professor Patricio Vela from Georgia Tech, and Wednesday 9 a.m. And we're looking forward to see like you next week.
Thanks again. Bye-bye.
Yeah, thanks. Thanks, Necmiye. Bye.